Geotechnical Engineering Part A, Soil Mechanics, Chapter 8, Seepage. Seepage in 3D. In mid-18th century, Pierre-Simon Laplace was born in Normandy, France, which he was a French scholar, a polymath. He did a great job in development of mathematics, physics, engineering, statistics, astronomy, and also philosophy. After 77 years, he died in Paris, France. This is French map, and you can see Normandy, and also Paris, which is almost 40 kilometers there. So, in many cases, we cannot solve the seepage through the soil by simple Darcy equation because most of the time we are encountering a situation that we have a seepage in two directions, so that's a kx and ky, both of them involved, so it's not only one dimension. And also most of the time we're not working with the uniform flow, so the only way to solve it is to use the graph solution to create the flow nets. And the concept of flow nets is based off one of the Laplace works, which is Laplace continuity equation. So let's see how that goes. It just says if there is a element of our study, water or fluid, the velocity of Vx enters here, and we have Vx plus deviation of Vx, either increasing or decreasing. And because we have a function based off x, y, z, and we want to make a derivation, that's a partial derivation of, for example, vx over x, partial derivation of vy over y, dr. Each of them is almost dvy over y, or separately you can call it like a normal derivation, but they are partial derivation because we have the function based off x, y, z, different parameters. So if we just consider the continuity equation which says q in, the same discharge comes to the our volumetric element should go out the same amount of water. So q in is equal to q out due to continuity of discharge. So, and if we just create the same pattern of equation for the other dimensions in y and z also, it just gives us a vz coming from z direction, and there is a change when velocity goes out, and there is other like vy and changes. Partial derivation of vy over y times dy. That's a seepage in 3D. Q in is equal to Q out. Discharge coming discharge is equal to going out discharge based off continuity equation. And if we just develop that Vx apply to this area, dy dz, the entrance area over here, we just project it here, and Vx is applied to the area of dy dz, the dimension of dy and z. So that's the back of that area. if we just develop the other areas as well, Vy applies to dx times dz plus vz times apply to the area. These are the appropriate area for y and z, likewise area for vx, and that's all q in. How about the velocity on the other side when the water goes out of our element, volumetric element? That's vx plus dvx over dx times the area. The change of velocity in y and change of velocity in z. Dx dy is our q out. If q in is equal to q out, then if you simplify that equation, you reach to an equation like partial derivation of vx over dx plus partial derivation of vy over dy plus partial derivation of z over dz equal to 0. That's differential format of continuity equation in a 3D format. So if we just consider it for a 2D seepage, it just says a dvx over dx plus dvy over dy is equal to 0. That's for a 2D. We just remove the third element of it. And at the same time, if we just expand our equation like a dx over dx, we can write it down like partial derivation or d over dx of k x times ix, and we do know I, d is equal to k times I. So we just expand dx like kx times ix and do the same for y and z. And we do know k is a constant, so we can take k out of the equation, and that says kx hydraulic conductivity in x direction is a constant, comes out of the derivation, then d over dx times dh over dx. We do know I itself, hydraulic gradient, is delta h, change variation in water head over the length of our travel. Delta h over delta l is our hydraulic gradient. In each direction. So Ix, for example, is a dH over dx in x direction for hydraulic gradient in x direction, that is Ix. If we just replace that in our equation like Ix, it just comes with a dH over dx. So it just turns to constant and a second order derivation. Do the same for the others like ky and kz, and it just gives us kx a constant, ky a constant, kz a constant, and d squared h over dx squared plus ky times d squared h over dy squared plus kz times d squared h over dz squared equal to 0. That's the 3D seepage equation. That's the 3D seepage equation. By solving this equation, we simply get the head of water in our flow, and by having H, as soon as we have the water head, we can calculate water pressure. So H is head of water in our flow, and U is water pressure. And the most important part we want to solve from, want to get the output of seepage equation, is either head of water or finally water pressure in soil, which we are interested in. So note 1, the importance of head calculation is when water is moving. In moving flow, we need to solve the seepage equation either in 2D format or 3D format to get the water head. So if it's not moving, so if it's in static mode, the water in stalemate or static mode, you just use the a piezometer or get the information from a data. So it means node 2 if then if we have a piezometric data, it is simple. So by just reading the piezometric data, we can get the head of water, then calculate U by H minus Z as gamma of water, can easily calculate the water pressure. But if you don't have the data of piezometric data about the head of water, there is no way to solve the seepage equation by the help of Laplace continuity equation. So in moving water, which is most of the case, we need to firstly calculate head of water, then based off the head of water, we can calculate water pressure in soil structure. We'll solve some example of 2 and 3D seepage in next videos. Thank you.